Good morning, everyone. I'm Wang. Currently, I'm a postdoc at Yale University and also a member of the FinAI community. So today, I'll introduce our recent work about the FinTagging, and I am ready benchmark for extracting and structuring financial information. So now I will follow the three parts to describe our task. The first part is the background. Every year, millions of financial reports are generated by companies across the globe, creating a flood of data for markets regulators. On the left, we can see the number of listed companies across major stock exchanges as January 2025, led by Japan, Canada, and the US. On the right, the map shows how reporting frequency varies by region, with most companies in the US, Canada, Japan, and India reporting quarterly, while Europe and China follow mixed schedules. With so many reports being filed so frequently around the world, the real question becomes, how do we make sense of all this data? That's why experts are increasingly adopting XBRL to bring structure and consistency to financial reporting. XBRL is a key technology that transforms financial reports from human readable formats like PDF and spreadsheets into structured machine readable data, and making them easier to analyze and compare across different companies. On the left, we see that without XBRL, investors must manually re-enter and process data from inconsistent formats. But with XBRL, the data can be directly imported and analyzed. On the right, XBRL also enable better comparability across companies by standardizing financial terms and making it easier to compare statements automatically. So how does XBRL works? Uh, so we can see the figure in the left. It shows the three steps process. Just giving the financial statement. This data is first tagged by accountants, then converted into a standardized XML document, and finally transformed into an XBRL formatted report. On the right, we see how the XBRL taxonomy defines relationships between financial terms like assets, liabilities, and equity, enabling structured data and automatic calculation. Each item is linked to a standardized definition and a monetary value, making financial data both machine readable and comparable. XBRL helps structure the data, but its quality still comes down to how accurately things are tagged. As these two charts show, tagging issues like leaf findings and data errors are still widespread, even among leading companies. On the left, we see that in 2013, a large number of companies either filed late or had to amend their findings, which suggests inconsistency and incomplete preparation before tagging. On the right, even for Fortune 500 companies, over 75% of findings have details errors, meaning the data lacked sufficient quality or structure, making accurate tagging more difficult. So what's a tagging? The tagging refers to the process of assigning standardized concept label or tags typically from the US-GAAP taxonomy to specify specific numerical facts in the financial document. Just as this figure shows, so given the tables or the context from the in the financial document, experts basically need to identify the meaningful values, numerical values from the tables or the sentence or context. Just as this sentence, the firstly the expert should identify the like $4.5 billion and $4.9 billion and $4.5 billion from this sentence, and assign the appropriate US-GAAP taxonomy concept just according to the taxonomy database, and also give some aside the entity type like monetary item type, as well as some other attributes like a period sign, just making to the structure format. So this structural labeling enables regulatory systems, analysis, and automated tools to understand, valid, and compare financial data crossing different companies. Uh, Tagging is clearly a critical step in the XBRL process, but surprisingly, there are only a few benchmarks that directly supported. On the left, we have two main benchmarks related to tagging, FinNI and FinXL. Beyond that, most benchmarks, just as shown in the right, target other tasks like entity and relation extraction, numerical reasoning, and structured text understanding. Now, we've seen most existing benchmarks focuses on financial QA reasoning or basic entity recognition. It's important to ask what are the limitations of these benchmarks when it comes to the real world XBR tagging and structured reporting. First, the task framing is overly simplified. Many benchmarks treat tagging as a flat multi-class classification problem, uh, using only around 1,000 US-GAAP tags, which falls short of the true taxonomy scale. Second, structured data is largely ignored. Most benchmarks exclude financial tables entirely, leading to poor alignment with real-world filing that involve complex text table interactions. So this table just compares several popular financial NLP benchmarks, and you can see here most of them lack taxonomy level labeling, structure extraction or concept linking, all of which are critical for high quality tagging in XBRL. To address these limitations, we introduced FinTagging, a new benchmark designed specifically for end-to-end financial tagging over real-world XBR filings. Our benchmark has three main contributions. The first one is the tagging enables end-to-end tagging. FinTagging enables end-to-end tagging across both financial tags and tables and converts the entire US-GAAP taxonomy. With over 10,000 labels, unlike a previous benchmark, it avoids flat classification and is LLM friendly by design. Secondly, we decompose this task into two key subtasks. The FinNI, which focuses on structured numerical information extraction, and FinCL, which handles fine-grained concept linking to taxonomy entries. The last one is we build a robust evaluation setup using real-world XBR filing analyzed by experts and release two data sets, the FinNI eval and the FinCL eval to jointly evaluate fact extraction, and concept link alignment. Now we introduce the FinTagging benchmark and its we will introduce the FinTagging benchmark and its components. So just look at how we formally define the XBRL tagging task. That is what exactly the model is expected to extract and predict from financial documents. So this is our overall task formulation. Just given a financial document D consisting of multiple textual contents and structured tables, a set of predefined value data types L specified by the XBRL specification, and a taxonomy database T containing a set of financial semantic concepts. The XBRL tagging task is to identify all relevant numeric values in D and enter each with the structured triplet format like fact, tab, and tag. The tag denotes the linked concept in T, such as US-GAAP, cash due from banks. The fact represents the extracted numerical value as it appears in the context, such as 2.5, 10,000, and so on. The type specifies the corresponding data type in L. Here we just predefined a five item type entity types here, such as monetary item type, percent percent item type, share item type, per share item type, and integer item type. Inspired by the information extraction and alignment works, and after discussed with financial reporting specialists, we formulate this task into two subtasks. Financial numerical identification, short as FinNI, and financial concept linking, short as FinCL. The FinNI subtask is our first subtask. It focuses on identifying numerical values in a financial document and assign each coarse-grained value data type. This corresponds to detecting the fact and the type components of each triplet, just like this, defined in the overall task. The second task is the FinCL task. The goal of this task is to semantically ground each identified numerical entity E by linking it to a concept C hat in the predefined financial taxonomy, which is the tag component of each triplet defined in the overall task. For the raw data collection, we collected 30 annual 10K reports filed in 2024 by publicly listed companies from the SEC. As shown in these tables, in total, there are more than 81,000 facts, including 69,000 for 451 linked to standard taxonomy tags, and 11,874 to SEC extension tags. Additionally, using the Beautiful Soup tool to parse these reports, we identified 76,835 narrative sentence and 5,450 financial tables here. To construct the FinTagging benchmark, we annotated a total of 3,355 sentence and 3,245 table sequence extract from the narrative and tabular content of the financial reports, collective financial reports, as summarized in the table 3. Among them, 1,627 textual instance and 2014 table sequence contain XBR tag information, so we treat it as a positive instance. While the remaining 1,726 27 texture and 1,231 table instance as negative samples. On average, textual inputs contains 82.55 tokens, whereas table sequence are significantly longer, averaging 999.74 tokens based on tokens. Based on this, we further construct two subtask specific data sets, FinNI eval and FinCL eval, just following the following three processing and sampling steps. The first step is the creation of numerical entity and US-GAAP concepts. Building on the initial filtering, the first step is we further refine the sentence and the table set to retain only high quality samples with gold standard annotations of numerical entity types and their associated US-GAAP concepts. We first exclude sentence and tables lacking US-GAAP labels. Then we conduct a statistical analysis of the types contained in the data, so we could predefine the most appropriate entity types for our benchmark. So just as shown in this figure, basically we identified 11 types of numerical entity types crossing the all 30 companies' financial reports. Among them, we found the top five types is most frequently and are consistently appear in all reports. So we select these five types as predefined entity types. And sentence and or tables containing these types are labeled as positive instance, while others are treated as negative samples. The second step, just based on the annotation produced procedure described in the first step, we construct the FinNI eval dataset comprising 6,599 samples derived from the annotated sentence tables. Specifically, the dataset comprised two components, the input block and the answer block. The input block includes task instruction and input content. The instruction defines the FinNI task by specifying the responsibilities of the LLMs and definitions of entity types and the rules to be followed. The answer block is formatted as a list light with the input block. The answer is a JSON list of all identified entity values and the types, or an empty JSON list. Just following the formulation of the FinCL subtask, we further construct the FinCL eval dataset that includes 52,572 query answer pairs for numerical entity normalization. In addition, we also built a US-GAAP taxonomy database containing 17,388 unique financial concepts. To create the FinCL eval dataset, we use all positive instance identified in the first step. Each query consists of a numerical entity, its corresponding entity type, and its surrounding context. while the answer is just is a associated US-GAAP concept. So here is our evaluation framework. This is our proposed unified framework for the FinTagging benchmark to exercise the performance of large language models on financial report tagging. As shown in this figure, given a financial report, the framework decomposes the task into two subtasks, FinNI and FinCL. The FinNI just identifies the numerical facts, facts and their types from narrative and the tabular content, while the FinCL links these identified facts to the most appropriate US-GAAP concept tags. The framework outputs the structure triplet, just like this, the fact time attack, enabling a joint evaluation of LLMs zero-shot capabilities in both factor information extraction and concept alignment. To provide the fair evaluation of overall benchmark performance, we just adopt a set of metrics focusing primarily on macro level and micro level evaluation strategies, just inspired by the previous works like FinNI and FinXL. For the FinNI subtask, because the objective is to extract correct entity type pairs, that is fact type pairs. So we use the parallel precision required F1 to evaluate this subtask performance. For the FinCL subtask, we only use accuracy to measure. So here is the model list that we use for our FinTagging benchmark. Just as shown in these figures, tables, we can see we use one general purpose closed source LLM, GPT-4o, and a general purpose open source LLMs like DeepSeek series model, Human series model, Llama series model, and Gemma model. One domain-specific financial LLM, such as FinO1, and also three pre-trained language models, such as BERT large, FinBERT, and SEC BERT. So now I will introduce our experimental results and do the briefly analysis. So the table 5 just presents the overall performance on our FinTagging benchmark. You can see from this table, it clearly demonstrates that under our framework, LLM effectively handle both frequent and rare financial tags, indicating their ability to mitigate long tail label challenges and underscoring the advantages of our information extraction and alignment formulation over traditional token level classification approaches. Because we just saw the macro level performance is higher than like the large models in the under the macro level performance is higher than other models, basically compared to the fine-tuned model, which means the large models under the zero-shot settings will pay more attention to every tags equally and not focus on the high frequently model labels. The table 6 just show the performance of various LLMs on the FinNI subtask. Overall, the larger models perform better at identifying numerical entities and generating structured outputs, even without financial domain training. DeepSeek V3 achieved the highest precision, record, and F1, outperforming all other models. In contrast, the smaller models like a Human 2.5 series model the score of this model below, we can see just below total 1 of 1 of score, highlighting their limitations in zero-shot settings. Interestingly, DeepSeek RY distill including 32 billion models show strong precision, suggesting that model design and distillation can help mitigate the impact of smaller scales. The table sum shows the accuracy of different models on the FinCL subtask. Overall performance is low, highlighting the challenge of fine-grained concept linking in finance. DeepSeek V3 achieves the highest accuracy, followed by GPT-4o, which all other models score below 0.11. Even large open source models like Cuban 2.5 14 billion and Gamma 2 27 billion underperform. The smaller models perform near random. This reflects the difficulty of handling complex taxonomies and subtle financial semantics. In the end, we also conduct the ablation experiment. So just to answer in this table 8, we can see that all LLMs fail completely with extreme classification, yielding zero precision, recall, and F1, confirming that the single-step choice among thousands of flat labels is not a valid LLM evaluation protocol. By decoupling extraction from concept linking and converting the full 10,000 more taxonomy, FinTagging produce meaningful scores and thus offers a far more realistic test bed for future model improvement. So in the end, we'll give the conclusion here. In our work, we introduce FinTagging, a benchmark for evaluating large language models on XBRL tagging of real-world financial reports. The benchmark comprises two subtasks, FinNI for financial numerical identification and FinCL for concept linking. Our findings show that while LLMs perform well on long-tail entities and generalize effectively in zero-shot settings, they struggle with accurate alignment to US-GAAP concepts, revealing limitations in schema-aware reasoning. The FinTagging provides a valuable foundation for future research in financial tagging and regulatory reporting. Yeah, that's all for my presentation. And if you are interested at our works, you can feel free to contact with me. And if you have any questions, we can discuss together. Yeah, here is our GitHub and Hugging Face. You can also read small details about our works from here. Thanks.